All right, let's dive into something huge. We're going to talk about building a system that can sift through these absolute mountains of medical data to predict when a patient might actually be harmed by their medication. This is a challenge with life or death stakes, so yeah, let's get right into it. So, this is the big question, right? Every single day, hospitals are just cranking out millions and millions of data points. We're talking lab results, doctor's notes, medication orders, you name it. And buried inside all that chaos are these tiny, faint signals of what we call adverse drug events, or ADEs. Finding those signals before they cause harm, that is one of the single biggest data science challenges in all of medicine. So, how in the world do we solve a problem that big? Well, the best way to think about it is this. We're not just building another database. We are architecting an intelligent hospital, but one that's designed purely for data. It's a place where raw information comes in the door, gets diagnosed, treated, and ultimately turned into life-saving insights. Now, every hospital, real or virtual, starts with a blueprint. And for our data hospital, that blueprint means choosing the right foundation, the data architecture that's going to support everything else we build on top of it. Traditionally, you really only had two choices here. On one side, you had the data lake. The best analogy is buying a cheap plot of land and just dumping all your raw materials there. It's super flexible, yeah, but it turns into a messy data swamp real fast. On the other side, you've got the data warehouse. This is like a perfectly organized library. Every single book is cataloged before it even hits the shelf. It's fast, it's reliable, but man, is it rigid and expensive to change. But today, we have this third option that is just perfect for our data hospital. It's called the Data Lakehouse, and it is literally the best of both worlds. It combines that cheap, flexible storage of the raw land with the powerful, smart organization of the library. This is the modern foundation our data hospital absolutely needs. And you might be asking, why is this so critical for healthcare? Well, it's because medical data comes in all shapes and sizes. You've got your neat structured data, like lab results. Then you have semi-structured data, like these weird hospital messaging files. And then there's the really tricky stuff, totally unstructured data, like a doctor's free text notes. A lakehouse is the only architecture that lets us store and, this is the key part, analyze all three of these together, which is essential if you want to spot a complex adverse event. Okay, so our foundation is in place. Now it's time to refine the raw data. I want you to think of this part like a mining operation, where our job is to turn all this messy raw ore into pure, valuable gold. This whole refinement process happens in three main stages. First up is the bronze layer. This is for the raw ore, exact, untouched copies of the source data. It's basically our safety net. We never lose the original. Next, in the silver layer, we start to clean things up, removing duplicates, fixing errors, and standardizing everything into a common format. And finally, you get to the gold layer. This is where you find the finished products, clean, analysis-ready tables that our algorithms can actually use to make predictions. So what does a gold table actually look like? Well, imagine a spreadsheet where every single row represents one patient for one day. And for that day, we have columns for things like their age, all the drugs they're on, special flags for high-risk medications like insulin, and even recent changes in lab values, like creatinine, which is a key way we track kidney function. This right here, this is the fuel for our prediction engine. Okay, having a great structure and a refinery process is a fantastic start, but there is a huge problem we haven't touched yet. What happens when the data coming from Hospital A and the data from Hospital B are in completely different languages? The solution really is to create a kind of universal translator. We need a set of common languages, or data standards as they're called, that allow all these different systems to communicate with each other flawlessly. Yeah, I know, this looks like complete gibberish. It's actually a really common data format in hospitals called HL7. And while it's nearly impossible for a person to read, buried inside that string of characters is a critical piece of information. This patient is on both aspirin and warfarin, a drug combo that dramatically increases their bleeding risk. Our system has to be able to read this and instantly understand what it means. And that's exactly where these standards come in. HL7 is the protocol that moves the data around. SNOMED CT, think of that as the giant dictionary of medicine. It's the thing that knows pneumonia is a type of lung disease. LOINC provides a universal code for every single lab test, so we're always comparing apples to apples. And ICD-10 uses billing codes to help us flag patients who already have high-risk conditions. Okay, so our hospital is built, our translators are ready to go. Now we actually need to stock the pharmacy. In other words, where are we going to get all this raw data from? The good news is there are some incredible public data sets out there for this exact kind of research. You've got synthetic data like SynPuff, which is kind of like the training wheels, great for getting started. There's the FDA's FAERS database, which has millions of real-world reports, but the big catch is it suffers from massive underreporting. And then you have the true gold mines, MIMIC and EICU. These contain incredibly deep, granular data from thousands of actual ICU stays, though, as you can imagine, you need special ethics training to get access. So we have the blueprint, the refinery, the translators, and the raw materials. We are ready to go, right? Well, not quite. Now we have to face what is probably the single biggest challenge in this entire field. Real-world healthcare data is just unbelievably messy. Let's start with this number. In some of these really rich ICU datasets, a lab test that's critical for detecting a deadly condition called sepsis, a test called lactate, can be missing for up to 88% of patients. That is a staggering amount of missing information for something so important. But here's the crucial point, and you have to get this. This missing data isn't just some random technical glitch. The very fact that a test is missing is itself a piece of information. It often means the doctor looked at the patient and decided, you know what, they don't seem sick enough to need this specific test. So the absence of data actually becomes a signal. The data can also hide these really subtle, dangerous biases. For example, take a look at this. Elderly patients, on average, have their vital signs checked much more frequently than younger adults. A machine learning model that doesn't know any better might incorrectly learn that more data equals a sicker patient, when really it just means more data equals an older patient. And that could lead it to totally underestimate the risk for younger people. And oh, the problems don't stop there. The quality of the data tends to get worse the longer a patient is in the hospital. Copy and paste errors are everywhere in doctor's notes, potentially hiding a new serious problem under a bunch of old text. And get this, just because a drug was ordered in the system, that doesn't mean the patient actually took it. Every single one of these is a potential landmine for our predictive models. So, after building this incredible data hospital, we're kind of left with this final, really provocative thought. This whole process, it's not just about analyzing the data we have. It's about learning to understand the profound stories being told by the data that isn't even there, and learning to listen to that silence. Well, that might just be the real key to predicting and preventing harm.